This is Precalculus chapter 5, lesson 4 on page 356. So the title of this lesson is Common and Natural Logarithmic Functions. Your common log has a base of 10. Here's your argument, and here's your exponent. This is your base. All right, such that it would be 10 raised to your exponent equals your argument. That's how we go back and forth. Now, you know that we can use different bases, right? But your common base is a 10. So if you just see something like this, you're saying 10 raised to some power equals 3. Okay? That's your common base. Your natural log is your ln. Its base is always e. We never write the e. It is assumed to be there. All right, because the base never changes like it can with logs. Base never changes for ln. It's always e. That means that it's this continuous compounding, this continuous growth or continuous decay. All right. So this would look like in exponential form. My base is e, my exponent is x, and my solution is 2. So here is the rule with logs. If I'm solving for the argument, if the argument is what I'm solving for, I'm going to exponents. All right? If I need to solve for the exponent, I'm going to logs. Solving for the argument, I'm going to exponents. Solving for the exponent, I'm going to logs. Okay? That's the rule. All right, so look at your first example on page 357. And it wants us to solve these without using a calculator. So the first one is the log of 1,000. Well, in my mind, here's what we want to know. What's the answer? This is 10 to some power equals 1,000. So it's 3, right? Because 10 cubed equals 1,000. All right, look at B. The log of 1. That's what it wants to know. What does it equal? Get a darker marker here. Well, this is saying 10 to some power equals 1. Well, it has to be 0. All right, so always when your argument is 1, if it's log, it doesn't matter what the base is, or if it's ln, 100% of the time, when your argument is 1, the answer is 0. Because anything raised to the 0 power equals 1. All right? Look at the next one. This is the log of the square root of 10. I'm going to rewrite this in exponential form. Be the log of 10 to the 1/2. All right, let's think about this in exponential form. Moving the log, writing the equivalent exponential statement. This would be 10 raised to some power is 10 to the 1/2. Well, when I have the exact same base, my exponents have to be equal. That's like saying 2 to the x equals 2 squared. What does x have to be? Well, it has to be 2 because 4 has to equal 4, right? So always when we have a common base, your exponents have to be equal. So, if I write e to the x plus 2 equals e to the 10, well, those exponents have to be equal. This value x plus 2 has to equal 10. All right, so what's the answer back here? It has to be 1/2. So always, when my argument is the same as my base, and maybe my argument is raised to a power. So let's just say it's log to the x of x cubed. It's when these two values are the same, the base and the argument, the answer is always the exponent. Same way, ln e to the 5, my base is e and my argument base is e. It's 5. All right, so when your bases and the base of your argument is the same, the answer is always the exponent. All right, so look at D. All right, so let's think about this. This is 10 to some power equals -3. Can I ever get a negative number when I raise something to the power? I can't, because even if I do like 10 to the -10th, right? That's just 1 over 10 to the 10th. That's a positive number. So literally, this value approaches 0. It's never 0. It just gets smaller and smaller and smaller. I can't even, this value can never be negative. Your argument can never be a negative number. If you did it in your calculator, you'd get an error. See, error. It doesn't work. So let's just make another point here. Can I ever have the log of 0? So can I raise 10 to any power and it ever equals 0? No, the number's just gonna get smaller and smaller and smaller. So by the same token, the log of 0 is undefined. So your argument will never be 0 to -infinity. It will always be this value. Your argument has to be, not including 0, 0 to positive infinity. All right? So D is undefined. Look at example 2. Can we write equivalent statements? So A is the log of x equals 2. Because the variable is in the argument position, we would always go to logs. My base is 10 squared equals x. Didn't ask us to solve it. What about if I have 10b to the x equals 29? Can we write an equivalent log statement? Yes, log. My base is 10, I don't have to write it. My argument is 29 equals x. All right, so I said this earlier. Solving for the argument, we're going to convert it to its equivalent exponential statement. Solving for the exponent, we're going to write an equivalent logarithm statement to solve for it. All right, so let's look at example 3. Natural logs. I already said this at the beginning. This is example 3 on page 358. We could do these in our calculators. It'd be ln 0.15. Here's your ln button. ln 0.15 equals. And there's your value. We go to 4 decimal places. 4 decimal places for logs. All right? You could do ln of 186. ln 186. These are all calculator. Right, just like for logs, your argument can't be negative. Same thing for natural logs. Your argument cannot be negative. So you cannot do the ln of -5. You'll get an error. It errors out. All right, look at example 4. Now we're going to solve by using an equivalent statement. Actually, example 2 did say solve, but you could have solved it. Maybe I should go back and solve them. Okay, so A, let's go back. Example 2, we're going to solve it. That's 10 squared equals x. X is 100. All right, this is back to example 2. This is the log of 29 equals x, and I can do that. That's the answer. Okay, now jumping forward to example 4, we're going to solve using equivalent statements. Either logs or exponentials, okay? ln of x equals 4. I don't know the argument, so I'm going to exponentials. All right, my base is e. The exponent is 4x. How do I get e on my calculator? It's second ln. Second ln puts e as your base to the 4th power. Remembering e is like 2.718. So x is 54. That's the solution. 4 decimal places. 4 decimal places. All right. B of example 4 is e to the x is 5. I'm solving for exponent. I know I'm going to logs. E is my base. I'm using the natural log. ln, there's my argument. I do not have to write the base of e. Equals x. I put ln 5 in my calculator. It equals, go to 4 decimal places. 4 decimal places. All right, graphs of logarithmic functions. Logs and exponents, logs and exponential growth, they are inverse functions. Remember, with inverse functions, we're swapping the x and the y. All right, so remember, with my exponential function, it always went through that point and looked like this. All right, with exponential functions, we swap our x and y. So instead of going through 0, 1, it's going to go through 1, 0. Okay, this is exponential. B raised to the x. This is logs. Okay, let's think about this. With exponential functions, my domain was all reals. All reals was my domain. My range was only above the x-axis, so that as x approached negative infinity, it got closer and closer to 0. But there's a horizontal asymptote at y equals 0. All right. So my range is from 0 to positive infinity, but it never equals 0. All right. With logarithms, they swap. My domain is not all reals now. My range is all reals. My domain, now we have this vertical asymptote. So as we get closer and closer to 0, it goes to negative infinity in terms of y. So my domain is now from 0 to positive infinity. All right, when we transformed our exponential functions, this is the point we moved. Left, right, up, and down. With logarithms, so we move for exponential functions at 0, 1. Well, other than, the vertical and horizontal stretches, the ones that are multiplied, all right? With logarithms, we're now going to move this point at 1, 0. That's the point we're going to move left, right, up, and down. All right? So, for logs, let's just look at all the possible transformations. All right? If I have a log of x plus 1 minus 3, this is the point that I'm moving. This is a horizontal shift, but it's the opposite. So it's a horizontal shift left by 1. All right, so from here, I'm going to move it here. This is a vertical shift down by 3. So I move it down by 3. So that now it looks like this and this. All right. So now this also changes my domain. I've shifted my domain back 1. So instead of, I'm going to draw it over here. So instead of the y-axis being that horizontal asymptote, I've moved it back to x is -1, is now that horizontal, like an asymptote, that it approaches but never equals. Got it? Okay, so let's look at example 5. All right, so we have h of x equals 2 times the log of x minus 3. Right here, just like our previous transformations, this is a vertical stretch by a factor of 2. So it's not going to pull it up. Instead of going like this, it's going to go more like that. All right, so that's what the vertical stretch will do. This is a horizontal shift. This is going to be right by 3. All right, remember my base is 10 because it's not there. All right, so we're gonna attempt to graph this. All right, this is the place I'm shifting, that 1, 0. So I'm going to shift it right by 3. So that's 1, 2, 3. I'm going to be at 4. So look, when x is 4 here, when x is 4 here, y is going to be 2 times the log of 4 minus 3. That's 1. Remember, the log of 1 is always 0. So that's 2 times 0. So that's 0. 4, 0. All right. I'm expecting there to be a vertical asymptote here. So let's get close. Let's go to 3.1. So it'd be 2 times the log of 3.1 minus 3. I'm just going to do this in my calculator. 2 times the log of 0.1 is what it's going to be. So it's going to be -2. That's going to be the y value. -2. So just right here is going to be here. All right, now let's just go to 5. When x is 5, it's going to be 2 times the log of 5 minus 3, or the log of 2. 2 times the log of 2. 2 times the log of 2. That's going to be 0.6, just barely above. So if I graphed it, it would look something like this, such that my domain has changed. My domain has been shifted from, in terms of x. So my domain was, remember, 0 to positive infinity. It's been shifted over 3. Now my domain is going to go from 3 to positive infinity. right? Because when I horizontally shift this key point over, I horizontally shift that vertical asymptote over. All right. That's example 5. Example 6. All right, look at example 6. Example 6, we have the ln of 2 minus x minus 3. And then we're going to talk about the domain and the range. All right, this is not in proper form. I can't have that negative. I have to factor that negative out, just like we did in all the other transformations. All right, so this is going to be a reflection, a horizontal reflection across the y-axis. So it's going to be reflected across the y-axis. All right, so instead of looking like this, it's going to look like that, okay? Reflected horizontally. All right, this is going to be a horizontal shift right by 2, and this is going to be a vertical shift down by 3. All right, so if you look at the image here, we're actually reflecting it across that new vertical asymptote. Okay, so from here, what have we shifted? Right by 2. All right, so that now here, right, there is my new vertical asymptote, and down by 3. 1, 2, 3, here. But instead of opening this way, it's going to reflect over here, and it's going to open this way. All right, and you can see the image in this figure. The bolder one is the transformed one. The other one is the original. All right, so we have this vertical asymptote that's been moved. All right, so now what is my domain? My domain goes from negative infinity up to positive 2. Has to be numbers less than 2. My range is all reals. Okay, the reflection does not affect the range. All right, look at example 7. How do we solve these types of equations? This is on the bottom of 360. All right. So we're given this formula where R is the rate and dr gives the time in years it takes to double. So dr is years it takes to double. So the years it takes to double equals the ln of 2 over the ln of 1 plus the rate. So we have two variables, time it takes to double and your annual rate. All right. So example A on the top of page 361. How long will it take? This is what we're solving for. How long it will take to double an investment of $2,500 at 6.5%. We do nothing with the $6,500. It doesn't matter what the money is. The rate determines how long it takes to double. It has nothing to do with how much you invest, okay? Because no matter what you invest, it's going to double. All right, so how long does it take for 6.5% to double is just the ln of 2 over the ln of 1 plus 0.065. You can put that in your calculators, and if you look in the textbook, the answer is 11.0067. So 11 years is what it would take to double. All right? Now look, so the formula would be given, okay? Look at B. What annual rate? Now we don't know the rate. So we have the ln of 2 divided by the ln of 1 plus the rate. That's what we don't know. In order for the investment in part A to double in 6 years. So that's what we want to know. In 6 years, how much will it take to double? Okay, if you remember, like I've taught you, the variable's in the denominator here. This is a real number. We can put in our calculators. This is a real number. I can swap my extremes. So I can say the ln of 1 plus r equals the ln of 2 over 6. I'm going to put this in my calculator. The ln of 2 divided by 6. I'm going to 4 decimal places. Actually, I'm just going to leave that in my calculator. All right, but I have the ln of 1 plus the rate equals 0.1155. I can now go to exponents to solve for my argument. So it's e raised to the 0.1155 equals 1 plus r. I'm going to do shift ln, second ln. I'm going to raise it to my previous answer. Right, clear. Second ln, and I want to pop in my answer, previous answer. Right, that's what I did. So I have that 1.1225 equals 1 plus r. I subtract 1, and my rate is about 12.25%. See, I'm just subtracting 1 from here, and so it's 0.1225, which is 12.25%.